So from last time, xi is the ith predictor. There's a reason why we call it the predictor. We'll talk about that later. Yi is the response. And this is an example. Clearly, the observations present a linear pattern. And I drew a line that's in orange. That would be my line of best fit. Good. The line of best fit has another name. From 2023, I can't believe I mentioned this, so don't even try it. It's not there. I know you know this. From 2023. Another name is least squares regression. Why do we call it least squares regression? We are trying to minimize the net error that we see. Now, where does or how do we assess the error? Let's pick a point. Which one should I pick? You pick. Tell me when.
When?
That point right there. I'm going to call that epsilon I. That is the theoretical value. So epsilon I is what we call the residual. In terms of expression, that would be yi minus yi hat. Agreed? Would it be okay to just look at one residual and be done with it? No, but a whole bunch of points. We've got to look at every single residual, which is why I indexed it with subscript I. Well, which points out of all these points do you believe would have the smallest residual? The one closest to the line. So I've got a bunch of candidates. That one, that one, that one. What's the three? Which one? What? This one. That's the closest one. Great. Now, mathematics, if things are close, then the distance has to be minimal, right? It's very small. Right. So yi minus yi hat is simply the distance. And going back to 2023, if you have an average and if you have an observation, xi minus x bar would be the deviation. Agreed. If you add all the deviations, what would the net result be? 0. In this case, this would theoretically be 0 because yi hat is the line that goes through the center. In other words, that is a line that sort of averages all the possible lines, goes through the middle. So clearly that is an average. And we know from basic statistics that if you take an observation, subtract its average, you get the deviation, sum them all together, you get 0. Well, if you start with 0, there's nothing to minimize. Do you agree? Yes. So we can't get 0. We are getting 0 because some of the residuals would end up being above the line, some below the line, add them together, it becomes 0. How do I get around that problem? I squander it. What is another way? Absolute value. Oftentimes, people might ask, well, I can simply do the absolute value. Why you square it? Well, from a distribution standpoint, probability distribution standpoint, dealing with absolute values is harder than dealing with squares. You're taking probabilities, that's that. So there might be a problem that the professor might put in there that involves absolute values. And you will see anytime we have absolute values, things are a bit complicated. We want to keep things simple. So we just want what does SS stand for? Sum of squares. The res part stands for residuals. Sum of squared residuals. I'm writing this as well because the book might simply use S instead of SS. Good. Okay. So you should know whether SS or S, they mean the same. I would intuitively go for SS because it's more standard. But I want you to know in this class, I write SS and sometimes mixture S. But if you see the homework and it says S, they are the same. I won't get into repeating stuff. You should know this from last time or from earlier today. So that is the theoretical model. And the estimated model yi hat beta 1 hat xi plus beta naught hat. Getting rid of epsilon I. Can you tell me why? So jealous, correct? Theoretically, epsilon I would become 0, so we can control that. Yes. But in practice, it is not going to be 0. It'll be somewhat small. That's what one would hope. Another explanation, simpler than that, without even getting into epsilon I.
Because you're estimating, so it doesn't have to be exact.
Okay, so because we are estimating, so it doesn't have to be exact, or since we are estimating, we sort of have an exact representation, which is correct variation. One more or the last one. The last. So since we estimated, I'm going to have a number here, I'm going to have a number there. That would be the orange line. The orange line doesn't have variability, correct? It's just a line. So there has to be no noise. With me so far? So I'm going to write that part. Yi, going to keep Yi as is, because I want to estimate the other parts. In other words, I want to know beta 1 hat, beta 0 hat. I'm going to expand that and write it as Yi squared. I have SS squares, I've expanded it, and I have that expression. But our goal is to evaluate those two values. We have to come up with those two values so that the net value should, so that we minimize that value. Do you agree? That is the difference between each of the observations, the response Yi from the fitted line, and we're going to estimate. We want that error, net squared error, which is sum of squared residuals, to be small, correct? In other words, we want to minimize the value. Going back to calculus 1, how do we minimize something? So to minimize an expression, to minimize a function, or to find where the minimum is, that is our ultimate goal. We want to find where the minimum is for that particular expression. We have to use derivatives. One of many ways to do this. As I mentioned during the first day of classes, we're going to start with the simple case, and when we get to the multiple case, we'll just switch over to matrices. That said, there are two variables, not just one. If it is one variable that I'm trying to estimate, it's easy. Simply use derivatives. Since there are two, what should we use? Still are going to use derivatives But a special case of derivatives. What is that? Calculus 3. Partial derivatives. So my first goal would be to take the derivative with respect to, I guess, beta naught hat. There is a reason why I wrote that as for this that. Sure, I can take the derivative of this expression, but we did certain things in calculus for a reason. Of the two, taking the derivative of this part is easier. What rule should you use? Chain rule. So the sum would remain because you can distribute the sum, can distribute the derivative through the sum. Treat whatever that is inside as is. Derivative of x squared is 2x. So 2 would come to the front and 2 minus 1 multiplied by the derivative of the inside. We are taking the derivative with respect to beta naught hat. So what is the derivative of yi? 0. Derivative of negative beta 1 hat xi? 0. Negative beta naught hat and minus. Good. Well, we want to set this equal to 0 and solve for beta naught. Beta naught hat. Good. Setting it equal to 0, I want to solve for beta naught hat. We'll divide by -2, and that's going to go away. So I simply have sum I equals 1 to n yi minus beta 1 hat xi minus beta naught hat equals 0. What is the next step? It's like everyone here is pulling a Gandhi. This is not a silent protest. I've got to say something. So negative times negative would be positive. Good.
explain that last little bit one more
Which one?
time? How you end up with positive sign in front of the sum of beta not has.
So do correct, it's not positive, that's negative. Well, leave this as is for now, leave that as is for now. What would that produce to? No I, but you are summing a constant n times. If you sum 3 2's, it's simply 3 times 2. I'm summing n beta naught hats, so n times beta naught hats. Beta 1 hat is a constant, so I'm just going to take that outside of the sum and put xi. So that expression is set equal to 0. So I can move that part to the other side. So I will have n beta naught hat equal to sum I equals 1 to n yi minus sum I equals 1 to n xi beta 1 hat. What is the next rational thing to do? Divide by n, so beta naught hat. I want to rewrite that expression in a nifty way. So what should I do? So that's the sample mean of y. That is the sample mean of x. What do we use to denote the sample mean? S. No. With the bar. Good. In 2023, Professor might simply have given this formula and say, plug it in, get the regression line. Great, but that's not the purpose of this class. Why is it so? This is the reason. So we can estimate the y-intercept, which is beta 1 hat, using an expression. Y bar minus beta 1 hat times x bar. But beta 1 hat, excuse me, beta 0 hat, depends on beta 1 hat. So we need to find beta 1 hat. Next step is to find beta 1 hat. To find beta 1 hat, we have to find beta 1 hat that minimizes our expression. So we want to take the partial derivative of the sum of squared residuals with respect to beta 1 hat. Give it a try. So if we take the derivative here, Same process, 2 is going to come to the front. Yi minus beta 1 hat xi minus beta naught hat times the derivative of inside. Yi is a constant, so the derivative is 0. I want to take the derivative of the second term. Xi is a constant. You're taking the derivative with respect to beta 1 hat, so I'll have negative xi. Negative beta naught hat is a constant. When we take the partial derivative with respect to beta 1 hat, that's going to go away. 0. So that's what I'll end up having. So negative 2. So negative 2, sum I equals 1 to n. Yi minus beta 1 hat, xi minus beta naught hat, xi. That is the expression we will have. We want to set that equal to 0 and solve for beta 1 hat. So negative 2 times sum yi minus beta 1 hat xi minus beta naught hat times xi equal to 0 divided by negative 2. Earlier, I mentioned that xy is a constant. We take the derivative. Well, negative 2 is a constant. I divided by negative 2 on both sides, got rid of it. If xi is a constant, can I divide that, on both sides and get rid of that? Yes. Just like I divided by negative 2, get rid of that like last time. Can I divide by xi and get rid of that too? No. Alison? No. Henna? Henna says no. Why? There is an I in it, so. So we can't get rid of that. Well, distribute the sum. So sum xi, yi minus beta 1 hat, sum I equals 1 to n, xi times xi squared minus sum I equals 1 to n, xi times beta naught hat equals 0. Almost there, promise. Good. We already estimated beta naught hat. So from previous results, I know beta naught hat is 5r minus beta 1 hat multiplied by x bar. So beta naught is a constant, so I can put it outside of the sum. I want to rewrite that sum I equals 1 to n xi. How? We did that earlier. So if you recall, x bar is sum I equals 1 to n xi divided by n. So I can rewrite the sum as n times x bar keep that to the side. Rewrite
Where did,
beta not hat. Yeah.
where did y bar minus beta 1 have?
I'm replacing. Because we solved for that earlier. So I'm plugging it back in. So sum I equals 1 to n xi yi minus beta 1 hat sum I equals 1 to n xi squared minus n x bar times negative y bar. So negative n x bar y bar. Negative times negative positive plus beta 1 hat n x bar squared. Good. I just distributed that n x bar up. I'm going to combine that term and that term, keep it on the left hand side, move everything else to the right hand side, because my ultimate goal is to solve for beta 1 hat. Minus n x bar y bar equals. Move this term to the other side, it will become beta 1 hat. I equals 1 to n xi squared. Move that term to the other side, minus beta 1 hat n x bar squared. Yes. What do we have in common? Beta 1 hat. So I would have sum I equals 1 to n xi squared minus n x bar squared. On this side, we'll have sum I equals 1 to n xi yi minus n times x bar y bar. How do we solve for beta 1 hat? Divide by that expression. So beta 1 hat sum I equals 1 to n xi yi minus n x bar y bar, entire thing divided by sum I equals 1 to n, x I squared minus n, x bar squared. Good. First thing that we did is we evaluated and found the estimate for beta naught hat, but beta naught hat depended on beta 1 hat, not just the data. So we went ahead and found the estimate for beta 1 hat by minimizing the sum of squared residuals, and I end up getting this expression. Look at this expression. This one depends purely on the observations, correct? No unknowns here. Everything is based on x I, y I. So the first step would be to find beta 1 hat. Once we find beta 1 hat using the data by itself, take this value, go back and put it in beta naught hat. And at that point, you know beta 1 hat, you know y bar, you know x bar, you can solve for beta naught hat. Does that make sense? Yes. So we have successfully evaluated beta 1 hat and beta naught hat. Where do we go from here? These expressions look pretty large. Not all of them, this one specifically. Now I'm going to rewrite this expression and put it in simpler terms so that it looks like the formulas from 2023, where you simply plug in and got the answer. Now you have a rationalization as to why you have those formulas. Again, the purpose of this class is to not plug in values to your TI calculator, but understand why things are the way they are. Good.